If a secondary star is present, its gravitational interaction could be sculpting the expanding gas, directing it along preferred axes. This would explain the sharp edges seen in the nebula and the apparent lack of chaotic turbulence that typically characterizes similar objects. The central star is likely in an advanced evolutionary stage, either approaching a transition to a Wolf-Rayet phase or nearing its final collapse. The material ejected into space could be part of a larger process in which layers of stellar atmosphere are shed over time, forming structured nebulae that persist long after the original outburst. The exact mechanism behind the symmetry remains a topic of ongoing study, with hypotheses ranging from episodic eruptions caused by internal instability to a controlled expansion influenced by a strong toroidal magnetic field. Spectroscopic analysis reveals that the nebula is rich in both silicate and carbon-based dust, suggesting complex chemical interactions occurring within its expanding shell. The presence of ionized hydrogen and oxygen lines indicates exposure to intense ultraviolet radiation, which is slowly altering the composition of the surrounding medium. These processes are crucial in enriching the interstellar environment with heavy elements that later contribute to the formation of new generations of stars and planetary systems. The velocity of the expanding gas in the nebula has been evolving for thousands of years, though it is unclear whether it has remained stable over time or if it has undergone significant changes in structure. Some researchers propose that the formation is an optical illusion, where a more cylindrical or bipolar outflow appears squared due to our viewing angle. Others argue that external influences, such as a dense interstellar medium or remnant stellar wind, reinforcing the shape by constraining material along specific planes. Advanced telescopes equipped with high-resolution spectrographs are expected to provide more precise data on the velocity distribution of gas and dust. By analyzing how light interacts with different regions, astronomers hope to reconstruct the three-dimensional shape and determine whether the observed symmetry is an inherent property or a temporary phase. If the central star is approaching a supernova event, its surrounding nebula could dramatically brighten as the explodes with the ejected material, similar to what has been observed in other massive star systems. Comparisons to other structured nebulae suggest that mass loss in massive stars follows patterns that are more organized than previously thought. While planetary nebulae often display symmetric forms due to the expansion of shells around dying stars, this particular object exhibits a level of precision that challenges conventional models. If magnetic forces are indeed playing a dominant role, it may suggest that similar structures could exist elsewhere, but remain undetected due to their orientation or distance from Earth. Infrared observations have also hinted at the presence of complex organic molecules within the nebula, which could have formed through photochemical reactions triggered by high-energy radiation. Such environments are thought to be crucial in the early stages of planetary system development, as they contribute to the formation of prebiotic compounds that later become part of interstellar dust clouds. Understanding how these materials evolve in different stellar environments provides insight into the chemical diversity of the galaxy. Future research will find the precise movement of gas within the nebula and other external factors are influencing its evolution. If a binary companion is confirmed, it could provide further evidence that multiple star systems are a key factor in shaping structured nebulae. Long-term monitoring may reveal subtle shifts in brightness or morphology, indicating ongoing dynamic processes that have yet to be fully understood. If the central star eventually undergoes a supernova, it could transform the surrounding region by sending shock waves through the nebula, triggering secondary reactions and possibly altering its structure. The resulting supernova remnant would provide valuable data on how pre-existing mass loss affects the aftermath of stellar explosions. If a neutron star or black hole forms at the core, it may interact with the surrounding material in ways that produce additional high-energy emissions, making it a potential source of radio waves or X-ray bursts. The precision of the formation continues to challenge existing astrophysical models, suggesting that either previously unknown mechanisms are at work or that magnetic shaping plays a far greater role in stellar evolution assumed. Upcoming telescopes with adaptive optics and interferometry will provide deeper insights into the processes governing the expansion of ionized gas and the interaction between radiation and dust within the nebula. While its ultimate fate remains uncertain, its significance as an astrophysical case study is undeniable. Whether it is a short-lived phase of stellar evolution or a long-standing feature that will persist for thousands of years, it rare and valuable opportunity to study the forces that shape the most massive stars in the cosmos. The answers it holds could refine our understanding of how stars evolve, how they lose mass, and how they influence the galactic environment over cosmic timescales. The forces responsible for shaping this nebula remain a subject of debate, with multiple mechanisms potentially working in tandem to maintain its strikingly structured form. The presence of a dense circumstellar medium suggests that earlier mass ejection events may have interacted with surrounding material, creating shock fronts that reinforce the observed geometry. If stellar winds or episodic eruptions from the central star were directed by an unseen companion, their effects could have compounded over time, gradually sculpting the nebula into its current configuration. Magnetic fields are another possible factor influencing its development. In some high-energy astrophysical environments, magnetic pressure can guide ionized gas along preferred paths, constraining the collimator-metric lobes. If this phenomenon is occurring here, it could help explain the sharp definition of the nebula's edges and the near-identical structure on opposite sides of the central star. Observations of other massive stellar remnants have shown that even weak magnetic fields can have a profound impact on outflow dynamics, reinforcing the idea that this nebula's shape may be magnetically driven. The chemical complexity of the surrounding gas adds another layer of intrigue. The discovery of molecular hydrogen and polycyclic aromatic hydrocarbons within the nebulous region has undergone prolonged exposure to ultraviolet radiation, leading to chemical reactions that produce complex organic compounds. If this material later becomes part of interstellar, it could contribute to the formation of planets or even prebiotic in future stellar systems. This highlights the role of evolved stars not only as sources of heavy elements but also as potential contributors to the early chemistry of planetary environments. The velocity distribution of ejected material is also a critical factor in understanding the formation of the nebula. If the gas is expanding uniformly, it would suggest that the star has been losing mass gradually over an extended period. However, if velocity gradients are detected, with some regions moving faster than others, it could indicate episodic bursts of energy, possibly linked to a hidden binary internal stellar instability. High-resolution spectroscopic studies will help determine whether the structure has remained stable or if it is actively evolving, with changes in brightness or morphology providing additional clues. Comparisons to other known stellar outflows provide valuable context for interpreting this structure. The similarity to bipolar planetary nebulae, which are often shaped by binary interactions, suggests that the nebula may represent an earlier stage of this process in a much more massive system. If future observations confirm the presence of an orbiting companion, it could provide strong evidence that binarity is a key factor in the formation of highly structured nebulae, challenging existing models of single-star mass loss. The possibility that the central star is approaching a terminal supernova phase adds an additional urgency to ongoing research. If this is a pre-supernova system, then the surrounding nebula may play a crucial role in determining the characteristics of the eventual explosion. A dense circumstellar medium could shape the supernova's light curve, producing an extended afterglow, or even influencing the type of remnant that forms. If the core collapse results in a neutron star or a black hole, the interaction between the compact object and the surrounding nebula could generate secondary emissions, including high-energy X-ray or radio bursts. Some researchers proposed that this nebula represents a previously unrecognized category of structured stellar outflows, distinct from both planetary nebulae and classical supernova remnants. If so, it could mean that highly organized mass loss occurs in more stars than currently expected but remains undetected in systems with less favorable viewing angles. Advanced three-dimensional modeling, combined with data from next-generation telescopes, will be necessary to determine whether similar formations exist elsewhere in the galaxy. Long-term monitoring will be essential to track any changes in the nebula's structure. If subtle shifts in brightness or gas distribution are detected, it could indicate ongoing mass loss or dynamic interactions within the expanding material. Alternatively, if the nebula remains unchanged over decades of observation, it would suggest that its formation was a driven event rather than active processes occurring in the present. Either scenario will provide valuable insights into how massive stars shed their outer layers and how those layers evolve over time. The nebula's role in the broader astrophysical landscape extends beyond its immediate surroundings. If it is indeed an example of a structured pre-supernova outflow, it could help refine predictions for other massive stars nearing the end of their life cycles. Understanding the processes shaping this formation could improve models of how supernovae interact with their environments, potentially leading to better interpretations of historical supernova remnants observed throughout the galaxy. Future research will focus on uncovering the underlying drivers of the nebula's symmetry, whether they be magnetic forces, binary interactions, or unknown stellar dynamics. Upcoming missions and observational campaigns will provide increasingly detailed data, helping to answer fundamental questions about the role of evolved stars in shaping the structure of the interstellar medium. Regardless of what mechanisms are ultimately responsible, the nebula remains a rare and invaluable opportunity to study the complex interplay between stellar evolution, mass loss, and the physical forces that govern the cosmos. As observational techniques continue to improve, new details about this enigmatic formation will likely emerge, shedding light on the precise mechanisms responsible for its near-perfect symmetry. The role of radiation pressure in shaping the expanding gas is an area of active investigation, as intense could be driving material outward along well-defined paths. If the star is emitting energy anisotropically, with stronger radiation in specific directions, it could be influencing the way ejected material disperses into space. This could help explain the structured nature of the nebula, particularly if interactions with a surrounding dust disk or magnetic field are reinforcing its geometric appearance. High-energy phenomena may also be contributing to the evolution of this structure. Some researchers suggest that the presence of shock fronts, regions where fast-moving gas collides with slower material, could be shaping the expanding nebula. These interactions create areas of increased density and ionization, altering how light scatters and giving the nebula its distinctive brightness distribution. If these shocks are being driven by periodic stellar outbursts, then the formation could be the result of ejection events, each adding to the overall complexity of its structure. Infrareds continue to provide new insights into the dust and gas composition of the surrounding environment. Data suggests that the dust grains within the nebula are relatively large compared to those found in diffuse interstellar clouds, possibly indicating that they have undergone significant processing due to radiation collisions. If this region is rich in carbon-based compounds, it could support the idea that evolved not only to heavy element enrichment but also to the formation of molecular precursors essential for planetary system development. Determining the precise nebula is another critical aspect of research. By analyzing the expansion velocity of different gas layers, astronomers aim to estimate when the initial mass ejection occurred. If the nebula is relatively young, it could be the result of a recent instability in the central star, whereas an older formation would suggest a more gradual mass loss process over an extended period. This distinction is important in understanding whether this structure is a transient phase that will evolve into a more diffuse remnant, or if it represents a long-lived phenomenon sustained by continuous energy input. The potential presence of a binary companion remains a crucial question, as its confirmation would provide a strong explanation of the nebula's ordered structure. If a secondary star is orbiting the central object, its gravitational influence could be built into specific flow patterns, producing the observed symmetry. Some models suggest that if a white dwarf, neutron star, or even a black hole is present, accretion-driven outflows could be responsible for the formation's striking shape. Identifying stations in the motion of the primary star indirect signs through X-ray or radio emissions may help resolve this mystery. Further study of the polarization of light from the nebula will be useful in determining whether magnetic forces are playing a significant role in its evolution. If light scattering patterns indicate the presence of aligned dust grains, it could suggest that a strong magnetic field is guiding the expansion of gas. Such as align with models of magnetically collimated outflows, which have other astrophysical environments, including young stellar objects and active galactic nuclei. One of the most instabilities is that this formation represents an edge of a process that has not been widely documented. If it turns out to a more well-known structure, such as a nebula or a supernova remnant, it could provide a unique opportunity to study how these phenomena nebula changes in the coming years will be crucial in determining its future trajectory, whether it will eventually dissipate into the interstellar medium or cling into a more complex structure. If the central star ultimately undergoes a supernova, the surrounding material could play in shaping the explosion's observable characteristics. The presence of dead matter could cause significant interaction between the supernova shock wave and the pre-existing nebula, leading to an unusually bright and prolonged event. If this occurs, it could offer direct observational evidence of influences the final stages of mass evolution. Long-term monitoring with next-generation telescopes will be essential in answering the remaining questions surrounding this structure. It's capable of resolving fine details in the gas distribution, magnetic field orientation, and spectral properties will provide the data needed to construct a more complete picture of its origins and evolution. If similar objects are identified elsewhere in the galaxy, it may indicate that these types of structured outflows are more common than currently believed, potentially leading to a re-evaluation of existing models of stellar mass loss. Regardless of its ultimate fate, this nebula remains one of the most visually striking and scientifically valuable examples of how complex forces interact in the late stages of stellar evolution. Whether shaped by binary dynamics, magnetic fields, episodic outbursts, or a combination of multiple factors, its existence challenges conventional astrophysical theories and offers an unparalleled opportunity to study the intricate processes governing matter. Future observations will undoubtedly bring new discoveries, deepening our understanding of how these cosmic structures form, persist, and eventually transform into the next generation of celestial phenomena. As observations continue to refine our understanding of this extraordinary formation, the interplay between multiple astrophysical forces increasingly apparent. The near-perfect symmetry suggests that a combination of stellar winds, pressure, dynamics, and possibly magnetic confinement is at work. Each of these factors contributes to shaping the expanding shell of gas and dust, maintaining its structural integrity over time. Whether this relation is an inherent property of certain types of stellar outflows, or a rare coincidence of conditions, remains an open question. Infrared spectroscopy has revealed variations in the temperature and density within the nebula, indicating that it is not a uniform shell but rather a complex, layered structure. This suggests that multiple ejection events may have occurred at different times, each adding a new component to the overall formation. If past eruptions have been episodically regulated by internal instabilities in the central star or interorbiting companion, the nebula's record of its progenitor's history. The detection of specific elements in the surrounding gas suggests radiation from the central star is actively altering its chemical. Regions exposed to the most intense ultraviolet and X-ray flux exhibit signs of ionization-driven molecular dissociation, while more shielded areas are molecules and dust grains. The environment provides insight insights into how massive stars influence theirs, gradually enriching the interstellar elements forged in their interior. One of the primary challenges in understanding the nature of this structure is determining whether it's symmetry, feature, or a long-term characteristic. If it is a recent outburst, it degrades over time as the expanding materials with external forces. On the other hand, if it is stabilized by ongoing processes, mass flow or a persistent magnetic field, it may remain largely for thousands of years. Tracking subtle shifts in the nebula's morphology over successive observational periods when distinguishing between these possibilities. Comparisons to other known nebulae suggest mass ejections are more common than previously assumed. The degree of symmetry here is exceptionally rating that specific conditions must be met for such a rise. If future surveys identify objects in different regions of the galaxy, it could provide a broad foundation for understanding how offers occur and what factor development. Numerical simulation used to model formation system. By incorporating variables such as stellar rotation and mass loss interactions to replicate the observed structure force evolution. Early results combine stellar rotation's gravitational influence flow patterns that resemble the nebula's prove accurate, a new perspective on the role of binarity in shaping circumstellar environment. Intriguing aspect is the future variability in the central star itself. If it is nearing the end of its evolutionary cycle, instability may lead to additional mass ejections or luminosity fluctuations. Such changes could provide direct observational evidence of it is being influenced stellar processes. If a sudden brightening event occurs, it could be a sign of an impending transformation, possibly signaling the transition into a Wolf-Rayet phase or even the approach of a Trojan. Ultimately elapse supernova, the surrounding nebula could pull in shaping the aftermath. A distinct medium could result in an unusually energetic explosion, with shock waves producing intricate interaction patterns within the already structured outflows. Such an event would be a rare opportunity to observe how massive stars influence their own supernova environments, offering insights into the processes that govern the final stages of long-term monitoring. Focus on detecting changes in velocity, ionization levels, and thermal emissions within the nebula. Any deviations in behavior could indicate nodes at work, potentially revealing governing stellar outflows. Upcoming space-based and ground-based observations providing increasingly detailed data, a clear remarkable formation to emerge. Whether this structure is an exceptional case or part of a broader, yet underappreciated category of organized mass ejections, its study is reshaping perspectives interact with their surroundings. The precise attaining its near-perfect symmetry remain one of the most compelling mysteries in physics, and future discoveries main pieces needed to nature. Regardless of what's come to light, this nebula stands as a striking testament to the complex and often unexpected beauty of stellar evolution. The persistent structured formation raises fundamental questions about the longevity of ordered nebulae and the mechanisms that sustain their geometry over time. If symmetry is not merely a transient effect, then ongoing processes maintaining its persistence. One possibility is that the radiation pressure from the central star is continually shaping the expanding gas, reinforcing existing structures and preventing dissipation. In this case, variations in stellar output could lead to subtle, but measurable shifts in the nebula's morphology, offering insights into how radiation-driven mass loss influences stellar environments. The presence of complex molecular compounds within the expanding shell suggests that chemical evolution is occurring on a large scale. As ultraviolet and X-ray radiation interacts with dust and gas, it triggers photodissociation processes that break apart existing molecules and encourage the formation of new ones. This cycle of destruction and recombination is key to understanding how massive stars contribute to the molecular diversity of space. If they can enable enough the synthesis of increasingly complex compounds, further enriching the surrounding medium. Velocity of the nebula's outflows is an area of investigation that may yield crucial insights into its formation history. If different layers of expanding at distinct rates, it could suggest multiple episodes of mass ejection, each contributing to the overall structure. By the motion of individual gas clouds within the nebula, astronomers can determine whether the expansion is accelerating, slowing down, or maintaining a steady rate. A uniform velocity distribution would support the idea of a single, well-coordinated outflow event, while irregularities could indicate ongoing dynamic interactions between different layers of material. The role of external influences, such as interactions with the surrounding interstellar medium, is also worth exploring. Expanding nebula is encountering regions of higher density gas. It could be experiencing external pressure that helps define its shape. This scenario is particularly intriguing because it would imply that the large-scale structure of the interstellar medium plays an active role in shaping stellar remnants. If such interactions are confirmed, they could offer a broader context for understanding how similar nebulae form across different galactic environments. Advances in computational astrophysics are enabling the development of increasingly sophisticated simulations that attempt to recreate the conditions necessary for such a structured formation. These models incorporate stellar rotation, magnetics, radiation binary gravitational effects. The goal is to determine a single dominant force is responsible for shaping the nebula. Factors are working together in a complex way. Early results suggest radiation pressure fields alone can produce flows of a binary companion, significant likelihood of maintaining long-term symmetry. Compact object is present within the system, it could further dynamics of the nebula. A star or black hole companion could be influencing the surrounding material through accretion or relativistic jets. These high-energy processes create additional structure, potentially explaining brightness or density variations observed. Observations detect X-ray emissions, fluctuations and radio signals. It may provide direct evidence of it playing an active role in the system. Another aspect of interest is whether this is a unique evolutionary path shares characteristics with other known structures that have been observed at different stages of development. If similar formations but have gone unnoticed due to unfavorable viewing angle, suggest that mass ejections are more commonly thought. A systematic structured nebulae uses telescope to identify additional examples, refining our understanding necessary for their formation. The long-term future of the nebula remains uncertain. Its fate will largely depend on the evolution of its central star. If the star continues at a steady rate, the surrounding structure may gradually expand and fade over thousands of years, blending into the interstellar medium. Alternatively, if the star undergoes a dramatic transition, such as collapsing into a white dwarf, neutron, or black hole, it could leave behind a comet that continues to interact with material. If this leads to periodic bursts of energy, the nebula may experience episodic reillumination, creating a variable emission profile that persists long after the initial mass ejection event. If a supernova does occur within the nebula, one of the most visually and scientifically interesting remnants ever observed. The pre-existing structure would shape the way shockwave propagates, creating patterns of glowing ionized gas. explosion could provide data on how mass loss before core collapse affects the properties of the supernova itself, offering a real-world test case for theoretical models of stellar death. Regardless of its ultimate fate, this nebula remains an astrophysical anomaly that continues to challenge conventional understanding. Symmetry, dynamic environment, and potential connection to high-energy astrophysical processes make it an ideal subject for continued study. The combination of observational theoretical modeling and future advancements promises to unlock further insights into the mechanisms responsible for shaping cosmic structures. In the broader context of stellar evolution, this nebula highlights the pathways that massive stars can take as they have life cycles. Represents a transient phenomenon or a more persistent stage of mass loss. It serves as a reminder that the processes governing the formation and evolution of stellar remnants are more intricate than previously assumed. As research continues, each new discovery will bring us closer to understanding the fundamental forces that sculpt the universe's most fascinating and mysterious celestial objects. As more data is gathered, the inks governing this structured outflow become clearer, yet many aspects remain elusive. The balance between stellar wind pressure, radiation forces, and gravitational interactions is delicate, and minor in any of these very significant nebula's morphology over time. If its current shape is maintained for an extended period, its ongoing regulating mechanism, possibly a combination of persistent mass loss cycles and external constraints imposed by either a magnetic field or a binary companion. Understanding of the internal motion of the gas cipherture is solving. If gas and dust are flowing outward at a uniform velocity, the nebula is eccentrically without significant turbulence. Within the outflow in acceleration, multiple processes are acting simultaneously. The present of these streams could point to local waves where it interacts with previous states. If the star at the center is rotating rapidly, it could also be affecting the mass ejection pattern. Fast rotation alters the stellar atmosphere, making it more oblate and enhancing equatorial mass loss through centrifugal forces. This would naturally produce an extratoroidal structure around the star, which could act as a framework for the broader nebula. If rotation is a key factor, then future spectroscopic studies of the star's surface may reveal Doppler broadening effects, indicating differential velocity regions across its surface. The role of ionization fronts within the nebula is another aspect of interest. If the central star's radiation is continuously exciting the surrounding gas, it may be forming stratified different elements are ionized at varying depths. This would lead to a multi-tiered composition where hydrogen, helium, oxygen, and heavier elements are distributed according to their ionization potentials. Understanding these ionization boundaries could provide insight into how far the star's influence extends and whether the outer regions of the nebula are still actively shaped by radiation or are mere structures from past eruptions. The possible presence of dust filaments or motes suggests that action phase elements and solid particles are occurring. Dust plays an important role in astrophysical chemistry as catalyst formation by providing surfaces where reactions can take place more efficiently. The nebula is rich in carbonated dust. It may indicate that material from the star is condensing into solid form, eventually contributing to the raw material for future planetary system formation. One key observational goal is whether the nebula is optically thick or if it allows significant amounts of radiation to escape. If it is largely transparent at certain wavelengths, then light from the central star may be escaping in directed beams, influencing surrounding interstellar clouds beyond the immediate boundaries of the structure. This could result in faint emission regions detectable in infrared or radio wavelengths, providing clues about how the nebula interacts with the broader galactic environment. The possibility of a faint, extended halo surrounding the main structure is also being explored. Some nebulae exhibit diffuse outer layer lower-density gas gradually into the surrounding medium. If the system follows a similar pattern, then it may have an extended outer envelope that is not immediately visible in current observations but could be revealed through deep exposure imaging techniques. If such a halo is present, it may contain older material from earlier mass ejections, offering a more complete picture of the star's long-term evolution. Further study of light polarization within the nebula may also help in determining whether magnetic fields are contributing to its structure. If dust grains are aligned along a preferred axis, it could indicate that an underlying magnetic field is shaping the flow of ion. Strong magnetic confinement why material appears to be expanding in a highly organized manner rather than dissipating irregularly, as is typical in many other stellar outflows. High-resolution radio observations could provide additional influence by detecting synchrotron radiation, which occurs when charged particles spiral along magnetic field lines. The long-term monitoring of the nebula's brightness and shape will provide important clues about its future evolution. If no significant changes are observed over the coming decades, it could suggest that the system has reached a stable equilibrium, where forces acting within it counterbalance one another. If gradual shifts in emission intensity or structural features are detected, it may indicate that the nebula is still undergoing active driven either by continued mass loss or external forces acting on the expanding shell. If the central star eventually transitions into degenerate remnant, such as a white dwarf or neutron star, its interactions with the nebula may take on new characteristics. A cooling white dwarf would emit lower energy, potentially altering the ionization structure of the nebula over time. If a neutron star or black hole forms, accretion of remaining material could generate episodic bursts of high-energy emissions, further complicating the evolutionary trajectory of the surrounding gas. With the advent of more sensitive astronomical instruments, including future space-based and ground-based telescopes, finer details of the nebula's composition and kinematics will become accessible. Multi-waves radio, and X-ray researchers to construct an increasingly refined model of the problem. This remarkable by extensional coverage to different regions of the spectrum, new physical interactions may be revealed, providing additional pieces to the puzzle of its formation and persistence. Understanding this nebula implications beyond its immediate structure. If similar objects are discovered in different star-forming regions or near other evolved stellar systems, it could indicate that such formations represent a recurring phase in the life cycles of massive stars. This would provide new constraints on theories of stellar mass loss and the role of binarity, magnetic fields, and radiation pressure in shaping astrophysical outflows. Each discovery would bring us understanding the universal principle transformation of stars and the lasting impact on their environments. As research continues, a fascinating subject at the intersection of multiple astrophysical disciplines. Its structured appearance challenges traditional models, suggesting that either previously unknown mechanisms are at work or that known processes are operating in a more complex manner than currently understood. The InSight system will not only refine our understanding of mass loss in evolved stars but may also influence broader concepts in astrophysics, from supernova formation of chemically enriched regions within galaxies. No matter what future observations reveal, this nebula stands as a striking intricate and often unexpected interactions that shape the cosmos. Persistence of such an intricate and symmetrical structure suggests that it is not merely a fleeting phase but a system governed by sustained forces. If merely the result of a single explosive event, its features would have begun to dissipate in a more chaotic fashion over time. Instead, the defined edge outflows indicate that ongoing mechanisms are reinforcing its structure, preventing it from dissolving into an irregular cloud. Understanding the nature of these stabilizing forces will provide crucial insights into how long such formations can persist and what role they play in the broader galactic ecosystem. One of the key aspects under investigation is whether the gas and dust within the nebula are interacting with interstellar magnetism beyond the immediate influence of the Sun. If so, the system may be embedded within a larger scale magnetized region that is influencing the distribution. This would mean that its shape is not solely the normal stellar processes but is also being conditioned by environmental factors on a much larger scale. The interaction of expanding nebulae with the magnetic field is a relatively unexplored area of research, but it could have profound implications for understanding the formation of structured outflows in other astrophysical settings. The possible nebula is part of a loop within a neighborhood is another avenue of study. If the central star is feeding particular clouds, it could be triggering secondary star formation in nearby regions. In this scenario, is not just a byproduct of stellar evolution but an active participant in the recycling of matter, enriching the interstellar medium and influencing the next generation of star formation. If observations detect enhanced star-forming activity in adjacent regions, it would support the idea that evolved contribute more directly to galactic chemical evolution than previously assumed. Infrared imaging continues to reveal variations in dust, grain size and composition, suggesting that material within the undergoing active processing. Appear more complex compounds, possibly formed through prolonged exposure to ultraviolet radiation. If dust grains within the nebula have been altered ionization cycles, they may exhibit unique spectral signatures that marker for similar objects elsewhere in the galaxy. By identifying the specific types of molecules present, researchers may be able to determine whether this environment is formation of organic precursors to planetary systems. The thermal structure of the nebula is another critical factor in assessing its long-term stability. If the gas within it is being heated unevenly, localized instabilities may form to subtle structural changes over time. High-resolution temperature maps created from multi-wavelength observations could reveal whether certain regions are cooling more rapidly than others, setting the stage for future condensation of material. If dense clumps are forming within the nebula, they could eventually collapse under gravity, leading to new stellar objects. While this would be an unexpected outcome for a system, it cannot yet be ruled out. The search for variability in the brightness of the central star remains. If the star exhibits periodic fluctuations in luminosity, it may indicate pulsational instabilities affecting its outer layers. These variations could, in turn, influence the mass loss rate, leading to episodic enhancements in the nebula's structure. If brightness changes are detected, correlating them with observed changes in the nebula's could help establish a direct link between stellar activity and the evolution of the surrounding material. The outermost layers of the nebula are of particular interest, as they may provide a record of its earliest formation state. If weak shock waves are detected propagating through the outer edges, it could suggest that the nebula is still expanding into previously undisturbed interstellar space. These shocks could be producing low-density that are difficult optical wavelengths but may be revealed through radio observations. If such features are confirmed, they would provide valuable clues about the nebula's expansion dynamics and whether it is still actively interacting with its environment. One of the most significant remaining uncertainties is whether this structure represents a phase that other massive stars undergo or if it is an exceptional case. If similar objects exist, but have not yet been identified, it could mean that such nebulae are more common than previously thought, but remain undetected due to observations. Systematic searches using telescopes with enhanced infrared and radio bands may reveal whether this is part of a broader class of stars that have gone largely unrecognized. If the nebula is a precursor to a supernova event, its surrounding structure may serve as a unique observational target when the explosion occurs. The interaction supernova shockwave and the pre-existing circumstellar material intricate patterns of emission, allowing astronomers to witness the complex interplay of stellar remnants and nebular evolution. The ability to study such unprecedented into how mass loss influences the properties of supernova explosions, helping to refine collapse dynamics. Continuing refinement of astrals incorporating observe from this nebula better understanding of the high-mass stellar environments. As computational capabilities advance, simulations will be able to incorporate increasingly detailed physical parameters, allowing researchers to test different formation scenarios and compare them directly to object data. If a definitive explanation for the nebula emerges, it will not only resolve one of the most intriguing astrophysical mysteries but also provide a framework for understanding similar objects that may be discovered in the future. Regardless of what new findings emerge, this nebula remains a compelling example of the complexity of stellar evolution and the diversity of structure arise from processes. Its continued study will provide valuable insights into how stars interact with their surroundings, redistributed throughout the galaxy, and how the final stages of stellar evolution shape the interstellar medium. Each new observation brings us closer to the full story, remarkable, revealing the intricate and often unexpected ways in which stars leave their mark on the cosmos. As research progresses, the long-term evolution of remains one of the most compelling. Structure will remain thousands of years, or gradually dissipate into the surrounding interstellar medium is still unclear. If the forces maintaining its symmetry weaken over time, the well-defined edges may begin to blur as expanding gas disperses. However, if there are persistent shaping mechanisms such as ongoing stellar mass loss, magnetic field interactions, or from surrounding interstellar clouds, the structure may remain largely intact for an extended period. Observations in multiple wavelengths continue to refine our understanding of the nebula's internal structure. Radio observations, for instance, are particularly useful in gas components components that may not be visible or infrared light. If significant molecular gas are present, it could indicate that the outer layers of the nebula, which may fumes or localized high-density regions, these structures and the surrounding environment, the distribution of heavier elements within the nebula of interest. If enriched nitrogen and carbon are concentrated in specific regions, it could suggest different rates fronts are influencing chemical processes. Detailed spectra may reveal earlier nuclear fusion central star, or if they are the result of more recesses in an unstable is determining whether it is interacting with external gas flows from other nearby stellar sources. Around the nebula, mass shedding could be expansion structure. This would suggest that nebular symmetry is not solely central. As interactions are detected, they could provide new insights into how massive stars shape their surroundings on a larger scale. The question of whether the central star is truly alone is unresolved. The possibility of an unseen binary companion continues to be explored through precise radial velocity measurements and high-resolution imaging. If a compact object, such as a neutron star or white dwarf, is orbiting within the system, its gravitational effects could be contributing to the organized shape of material. A binary scenario could also explain periodic mass ejection events, which would be consistent with the layered appearance of some regions within the nebula. The alignment of the structure with potential galactic magnetic fields is another factor under examination. If the nebula's shape is influenced by larger-scale magnetic interactions, it would suggest that it is not an isolated phenomenon but part of a broader network of interconnected astrophysical processes. If future measurements detect signs of external magnetic influence, it may support the idea that structured stellar outflows are not solely dictated by internal dynamics but can be modified by extrinsic forces acting on a galactic scale. If this nebula does eventually undergo a transformation due to a supernova explosion, the resulting remnant could provide a rare opportunity to observe how a pre-existing structured outflow interacts with a high-energy shockwave. Such an event would likely produce an asymmetric supernova remnant, with expanding material encountering some directions while escaping more freely in others. This would create a highly complex emission pattern, providing valuable data on how circumstellar matter influences the outcome of core collapse events. Even if a supernova does not occur in the near future, the nebula's gradual evolution important insights into how mass loss continues in late-stage stellar systems. Long-term observed changes in its brightness, expansion rate, and spectral properties, revealing whether the structure is gradually dispersing or if it remains dynamically active. If the nebula continues to exhibit stability over time, it may challenge existing ejection and suggest unrecognized stabilizing mechanisms are at work. Future telescopes, particularly those designed for high-resolution spectroscopization studies, will be instrumental in unraveling the finer details of the nebula's composition and motion. By studying variations in emission across different regions, astronomers terrific forces, such as localized shock waves or radiation pressure differences, are influencing its evolution. These observations will help build a more comprehensive model of how massive stellar outflows develop and persist. This nebula remains a case study for astrophysics, not only because of its striking appearance but because of the numerous unanswered questions surrounding its origin, stability,